Welcome back to Mechanical Design 1 course. We'll continue with the stress, strain, and deflection topic. Combined stresses. It's very common in machine parts to have combinations of loading that create both normal and shear stresses on the same part. There may be locations within the part where these applied stresses must be combined to find the principal stresses and maximum shear stresses. So far, mostly we had uh, independent stresses applied independent stresses on the part. For example, we had axial tension, we had axial compression, or we had shear stresses or transverse shear stresses, or we had shear torsion stresses. So these type of loads could be combined in real scenarios, and we want to see how we could combine them, how we could analyze them in coming examples. So we'll continue with some examples to understand the materials we already covered so far. Question. We have a stress element with sigma x, sigma y, and tau xy of 16.9 and 5 kilo psi, and psi is pound per square inch. And we want to find principal normal stresses and principal shear stresses, and find basically the angle of principal coordinate systems compared to the applied coordinate system. So this is applied coordinate system, okay? And we want to see in what angle we will have our principal coordinate systems. So in past, we had example of axial axial compression or tension stresses, or we had the pure torsion. And on those examples, some of these elements were zero. But now we could see in this example, we have all the elements and none of them are zero, and see how we could deal with that, okay? So we need to use Mohr circle or formulas that we already presented. And of course, Mohr circle is more intuitive to understand and easy to implement. We don't have to memorize any formulas if you use a Mohr circle. We need to start with our stress element and put our stresses on that. So we have both sigma x and sigma y positive plus tau xy, okay? But be careful that this tau xy is positive based on a stress tensor matrix, okay? So it's positive in the tensor stress matrix, but not necessarily in the Mohr circle. And the Mohr circle, we need to follow the convention of the Mohr circle for each side, I mean the x or y side of the cube. Okay, so if it's positive, it means that basically the heads are intersecting, okay? So the head are intersecting here, and tau xy on the x side is willing to rotate the element counterclockwise, and tau xy on the y side is willing to rotate the element clockwise. So based on the Mohr circle convention, we need to first find the point sigma x tau xy, okay? And this is the sigma x tau xy, okay? So sigma x is 16, okay? This is the sigma axis and this is the tau axis. And the tau xy here is negative because basically it's counterclockwise, it's willing to rotate this element counterclockwise, or basically it tends to rotate the element counterclockwise. So it falls into the negative territory of the y axis or the tau axis here. So we have our first point. The second point will be sigma y tau xy, and tau xy on this side is positive because it rotates the element clockwise. So we have 9 and 5. So now we have our 2 points, or A and B points, as we labeled them in the previous slides. And what we need to do now, we need to connect them to find the C point, calculate the C point, which is the middle point on the sigma axis, and is 9 plus 16 divided by 2 is 12.5. The next we could find CD distance here, okay, which is 16 minus 9 divided by 2. Okay, so see the difference between these two. One has plus, the other one has minus. Okay, so C and CD. Now we have the CD. Now we need to find R, or the radius of our circle. Okay, and the radius of circle could be easily calculated by having CD and tau. Okay, so we have this right triangle here. This right triangle, we could find the radius of circle. So R will be square root of 5 square plus 3.5 square, and is equal to 6.1. Now we have R. So basically we are trying to find the geometry of the Mohr circle, yes? Now we need to find the sigma 1 and sigma 2. It will be easy. It's C plus R and C minus R. So sigma 1 is C plus R and is 18.6, and sigma 2 is C minus R and is 6.5. Look here, that sigma 1 and sigma 2 could be negative or positive, or one of them could be positive and other one negative. There is no any limitation on from this aspect. Phi, now we want to find phi. Now we have our principal normal stresses and principal shear stress is this tau 1. It's equal to R, and we already calculated R is 6.1. Okay, so now we want to see what is the angle between principal normal coordinate system and or applied coordinate system. So we need to find this angle phi p, or phi principal. Okay, and as we said, angles on Mohr circle is twice real angles. We have this right triangle here, so we could easily find phi p by or 2 phi p is equal to tangent square of 5, which is this side of triangle, divided by 3.5, or this side of triangle, and we could find phi p. Okay, so see what is the direction of rotation. Is it clockwise or counterclockwise? Okay, it could be both. It depends on which side of the cube wants to be rotated. So for example, if we want to rotate the x side, okay, x side, we need to go counterclockwise, and then that basically coordinate system, or the x coordinate system, now will be sigma 1 coordinate system. Or we could say the stress on this side of the cube now will be equal to after rotation, yes, this side of the cube will have a normal stress equal to sigma 1. Okay, of course, you could also rotate it from this side. You will end up with the same cube, but you should be careful that what's happening exactly. If you are rotating from this side, then the sigma y will be equal to sigma 2, but you will end up with exactly the same figure, same stress element. Okay, so this is a cube with a principal normal stresses and principal normal coordinate systems. You see that the tau or shear stress on this element will be 0. Why? Because these 2 points now don't have any y component or tau component. And this is exactly definition of principal normal stresses, that the shear stress must be equal to 0. Now we want to find a principal shear stress element. What we need to do, we need to find phi s, see how much we need to rotate applied coordinate systems, and we see that 2 phi s plus 2 phi p is equal to 90 degrees. So phi s is equal to 45 minus phi p, and will be equal to 17.5. Okay, and here again we need to be careful which side we are rotating. If we are rotating the x side, then the direction of rotation will be clockwise. See, this is a clockwise rotation, and the normal stress on the x side will be equal to c. And shear stress will be equal to tau max or tau 2, which tau 2 is also equal to tau 1, yes? Here you see that we have a stress, the normal stress equal to C, which is 12.5, and we have a shear stress, which is negative based on the Morse convention. It means that it tends to rotate or cube counterclockwise. On the y side, now the y basically point sits on this point. You see that the normal stress will be equal to C again and is equal to 12.5. And the shear stress is clockwise. It tends to rotate or a stress element clockwise and will be equal to R or tau 1, which is 6.1. Okay, so this is for one stress element, okay? This is when we know how much is stress on one stress element. And again, I remind you that the one stress element or one of these cubes represent 1 point of a part, okay? This is just 1 point in a part. Now we want to see how we could find also apply the stresses based on the knowledge we developed so far for different scenarios. For example, bending for the bending moment, yes, for the normal stress that is caused by bending moments, or a shear stress due to transverse shear, or shear stress due to torsion torques. Yes, so we developed this knowledge. Now we want to see how we could apply the stress on a real part. Okay, so this example will show us. Okay, we want to find the most highly stressed locations on the bracket shown in figure and determine the applied and principal stresses at those locations. So it's very important to find highly stressed location. So we have this bracket, and this bracket is a rigid bracket uh, welded or fixed to a wall. Okay, and the force here is applied on the arm of the bracket. But we want to see if this bracket could hold the load and could survive under the specific load or not. Okay, so later in coming chapters and discussion, we will see based on failure theories, either static or dynamic failure theories, we will see if a part could withstand the loads or not, or it will break under the load or not, okay? But if we want to use those theories, we need to first find the critical points. A point that has a maximum stresses or maximum principal stresses or shear stresses. But which point has that maximum stress? Yes, intuitively, practically, we could guess that basically the base will withstand the maximum stress. So point A or point B should be investigated. Why? Because the base will go under the maximum bending moment. Okay, so the maximum bending moment happens at the base. Okay, so we need to first find a critical point because it will be very tedious to examine and investigate all points on a part. Yes, it's almost impossible. Of course, can be done by FEA analysis and softwares, but if you want to do it analytically, we don't have to examine all points of the part. Yes, we need to find a point with the maximum applied stress, and we know here that the base goes under maximum bending moment. Okay, let's back to our example. The rod length L is 6 inch, so we have L and arm A is 8 inch. The rod outside diameter D is 1.5. Okay, so this D is 1.5 inch. And the load F is 1,000 pound. The load is static, and we want to consider shear due to transverse load. So what we need to do, we need to go and look at the free body diagram and find a bending moment and find a shear force and a torsion torque, okay? So here we have our bracket again. On the base, the shear force will be equal to F, which is equal to 1,000. So you could treat basically this rod as a cantilever beam, and based on the beam analysis, you could find a shear force and the bending moment across the beam. But if you do so, you will see the maximum bending moment happens on the base, and the shear force is constant across the beam. So maximum bending moment at the base is equal to F multiplied by L. Okay, and L was 1 inch, so that will be 1,000 pound inch. And the torsion torque is equal to F multiplied by A. Okay, so this is the arm of the torque, and F multiplied by A will give us the torsion torque. And is constant across the beam, will be constant for all cross sections of the beam. It will be constant, and is equal to 8,000 pound-inch. Okay, so we have done our force analysis, and we know what are our forces and moments. And now it's time to calculate our applied stresses. Okay, before going to the applied stresses, we could find a second moment of inertia and polar moment of inertia for the beam. Okay, and that comes to basically these equations. Because we have a circular cross section, you could refer to the appendixes of the book for different cross sections. But for solid circular cross section is equal to pi d4 divided by 33, and j is twice I because it's basically symmetrical on the x and y axis. So j is equal to 2I for the case of solid circular cross sections, or is equal to pi d to the power of 4 divided by 64. Okay, so we've done these calculations. About these graphs, as we go forward, we will discuss them. The first one shows a bending normal stress distribution across the beam, and we are specifically focusing on the base cross section here that includes A and B points. And the second one shows a transverse shear stress distribution that we already discussed this, which will be 0 at the top and will be maximum at the middle or at the neutral axis. So at the point A will be 0 and at the point B will be maximum. And this one shows a shear stress distribution due to torsional torque, okay? And you could see that is equal at the point A and B. Now we need to investigate both point A and B to see which one is the most critical point, because the bending moment will be equal or the same for both of these points, but in terms of stress, as you could see, they have a different stress element, and mostly because of the bending normal stress distribution and the transverse shear stress distribution, because at the point A we have a maximum bending normal stress, and at the point B the normal stress will be 0 at the neutral axis and will be completely opposite in terms of transverse shear. Okay, so we will discuss the stress element on each of these points in coming slides. Okay, so first let's do the analysis on point A. Here we have our cross section at the base that includes point A and B, and for each of these points we have a stress element. Okay, so this is the gray square here shows the stress element. And each of these elements need to be completed by stress components. So this is a stress element at point A, and this is a stress element at point B, okay? So this cube is this square here, and this cube, this square here. Also be careful of the coordinate system, since the x axis is perpendicular to our surface. All this subscript starts with the x, and we need to see the second subscript. So second one shows the direction of stress. For the normal stresses, we said that we reduce subscripts to 1, so we only have one, sigma x, and we see for the tau x z, I will explain it. Okay, so first for the sigma x, we have a formula which is mc divided by I, and we found mc is the r is r or d divided by 2, is the distance from the center to top fiber, okay, this distance here, okay. We calculated I already, and now we have a sigma x. So now we have our sigma x here on stress element here. Now we need to find sig tau x z. Okay, so why do we call it z? Because the stress here, the stress due to transverse shear is in the direction of sorry, at the point A, the shear due to transverse shear, shear force is 0. Okay, so at the point A, we don't have a stress here, but we have shear stress because of torsion torque. Okay, so the torsion torque formula was TR divided by J. We calculated torsion torque. R is the radius of the cross section, and we calculated J. Okay, so about the second subscript, it could be either Z or Y, but which one is that? We need to see what is the direction of this shear stress, and let me show you here on picture. So so here we have our basically the direction of the shear. Okay, so this is a shear shear stress. Okay, so at any point basically we could see, and these are narrows that follow each other, arrows that follow each other. So you see that what is the direction of the tau? It's basically on the direction of the z-axis. Okay, so this one is tau xz. The first subscript, again, because it sits on a plane which is perpendicular to the x-axis, and the second one shows the direction of the tau. Now we have is sigma x and the tau xz, and as I said, the shear stress because of the transverse force will be 0 at point A. Okay. Now we have our full stress element at point A, and we could use more circle to find the principal normal stresses and principal shear stresses, and basically accomplish or stress analysis on point A. Okay, so we'll do so. I wish you and recommend you, suggest you to use more circle also. Okay, not only look at these formulas, also use more circle to fully first understand more circle, plus you will see that you don't need to memorize these formulas. So if you use a more circle, we could find the tau max, which is principal shear stress. We have sigma x and sigma z on the element. You see that sigma z here is 0. Okay, sigma z is 0. Okay, so we will reduce, or we could reduce this cube to a square with the x and z coordinate system. So sigma z is 0, and tau x z and sigma x is already calculated. Now we have tau max. We could find sigma 1, sigma 2, and sigma 3, and sigma 1 is sigma x plus sigma z divided by 2 plus tau max. Sigma 3 is sigma x plus sigma z divided by 2 minus tau max, and sigma 2 is 0. Okay, sigma 2 is 0. Okay, so now we have sigma 1 and sigma 3, or on or square element here. We could easily basically represent or sigma 1 and sigma 2. We could also find, based on the Moore circuit, we could find the direction and angle we need to rotate applied coordinate systems to find a principal coordinate systems. Okay, as we represented in the first example. Okay, so we are done now with the stress analysis at the point A. Okay, and we could now continue for the point B. Why do we need, again, I'm gonna back to the top view and see why do we need to do investigation on both point A and B. Again, because we identify the critical cross section, we know that the base cross section has the maximum bending moment, but in terms of stresses, we are not sure that which point on that cross section is the most critical one. Okay. Okay, now let's continue with point B. Sigma x is my divided by I. Y is the distance from neutral axis to the target point, yes? So for the point A, y is equal to c or b divided by 2, or the radius of the circle. But for the point B, that distance y is equal to 0. Okay, so sigma x will be equal to 0. Shear force because of the torsion torque is equal to TR divided by J, and is similar to the point A, and is equal to 12,072 psi. And now we have a shear force because of the transverse load. This one could be calculated by different methods. But we already developed this formula for specifically circular cross sections, and it's 4V divided by 3A, and A is the cross sectional area, okay, or ER squared pi R squared. Okay, so we have A, we have V, and the tau transfers could be also calculated. So the overall tau xz is summation of the shear force because of torsion and transverse load. Okay, and that basically happens here. We could see we have both on the same direction. We said that the direction of the shear force because of the transverse load is basically downward and sits on the surface, and it's same as the torsion torque. Okay, so they will have exactly the same direction, and we need to sum them up. Okay, so the overall tau xz will be equal to 12,827 psi. Now we need to move on to the Moore circle and see how much is principal normal stress and shear stress on point B. Okay, so here we need to first complete the stress element at the point B. We see that there is no any sigma x is 0. We only have these two shear stresses. One is 4V divided by 3A, the other one is TR divided by J, and these two shear force stresses should be adding, and now we have tau xz. Okay, or we could say that point B is in pure torsion. If we use more circle, we have basically sigma x and sigma z, and tau xz. These two are 0. We calculated tau xz, and tau max will be equal to tau xz. Sigma 1 and sigma 2 could be also calculated by more circle, and we see that the sigma 1 is equal to tau max, and sigma 3 is equal to minus tau max. Okay, and now we could compare point A and B and see which one has a maximum principal normal stress. I'm going to leave that part to you, and that could be used as a criteria for a vulnerable point. Which point is the most critical point? We will develop knowledge and the theory in coming chapters to see which part or which point of the part will break first, based on the failure theories, static and dynamic, which is the case for the static case, or failure theory for the static stresses could be applied on this bracket because the force also is in a static mode. Okay, so we are now we are done with this example, and we could move on to another one. So in this example, we have a similar bracket, and we want to determine the bending stress at point A and the shear stress due to transverse loading at point B. Also find torsional shear stress at both points. Determine principal stresses at point A and B. So why again point A and B? Because this cross section at the base goes under maximum bending moment on these examples. Yes. For other examples, we need to do bending moment and the shear force analysis across the beam and see which cross section is the most critical cross section in terms of maximum bending moment. But this one is a cantilever beam, and is quite obvious that the base cross section is the critical one. Okay, so we have geometrical parameters here and the force, and we will use these numbers for our calculations. This is a free body diagram, and this is the base. You see the reaction force R and the bending moment and the torsion torque. We need to find these ones. I'm going to go through this example quite quick because it's very similar to the previous one. R, the reaction force, will be equal to the force F. Reaction moment M is equal to F multiplied by L, and the distance from neutral axis to outside of tube, or CT, it's half of OD. Torque on tube, or torsion torque on tube, is F multiplied by A. Okay, moment of inertia, this is a hollow circular cross section, could be calculated by this formula. Again, you could refer to the appendix of this book for different cross sections, and polar moment of inertia is twice I for this hollow circular cross section. Okay, so we've done the force analysis, and we calculated some geometrical parameters. Now we could continue with the stress analysis. For the point A, sigma x is mc divided by I, and the tau xz is TR divided by J. Do the calculation yourself and confirm these numbers. Okay. So we have our stress element at point A, apply the stresses at point A. So at point B, sigma x is my divided by I, y is 0. So sigma x will be 0, tau torsion is TR divided by J, cross-sectional area A could be calculated easily, and we have a maximum shear, and the maximum shear due to transverse load or V could be calculated. And finally, we have tau xy, which is tau torsion minus tau transverse. I'm going to leave that part to you to understand why is first negative here and why the second subscript is y for the point B. Now we have applied the stresses at point A and B. And what we need to do, we need to use a Mohr circle to find principal normal stresses and shear stresses for both point A and B. I'm going to leave that part to you. It's very similar to the previous example. So follow the same methodology to find a principal stresses on both point A and B and see which point is more vulnerable to failure, okay? So we are done with the examples, and from the second slide, we'll move to another topic.